Assalamu alaikum. Welcome to the class of signals and systems. So before midterm, we discussed Fourier series representation of periodic signals. And we found that if in continuous time, if signal shows periodicity, then we can represent that signal in a mathematical form, and that mathematical form is known as Fourier series. So let me revise the two equations that we derived for representing any continuous time periodic signal. So if there is a signal, continuous time signal, x of t, and if it fulfills this condition, then we can represent in terms of Fourier series. And there are two equations that are part of Fourier series. So first equation is x of t represented as summation over k from minus infinity to plus infinity. Fourier series coefficient a sub k used to power j k omega naught. We can also represent this equation by another form, and that is representing omega naught in terms of period. So we can also say that Fourier series is equal to summation over k from minus infinity to plus infinity, a sub k e to the power jk 2 pi divided by capital T, where capital T is the fundamental period. And the other equation is the equation for Fourier series coefficients, ak, which is equal to 1 over t, then integration over an interval equal to the time period of the signal, x of t is to the power minus jk omega naught. Or in a similar manner, I can also write this equation in terms of period, that is e to the power jk 2 pi divided by capital T into t. So these are two equations that we have covered in our previous lecture. And you also remember that this equation is known as synthesis equation, and this equation is known as analysis equation. And these coefficients are known as Fourier series coefficients, or we also call them as spectral coefficients. Spectral coefficients of x of t. So this idea of representing a given periodic signal x of t in this form was first proposed by Fourier. And I also mentioned that when Fourier first proposed this idea, there was a lot of resistance to his idea. But ultimately, after a lot of research from other scientists, we now know that not all periodic signals can be represented in Fourier series. And in our last lecture before midterm, I talked about those requirements that periodic signal must satisfy so that we can represent it in this Fourier series representation. We talk about conditions, and the most commonly used conditions are Dirichlet conditions. And at the end of that discussion, I concluded that it is true that Fourier was not correct that any given periodic signal will have a Fourier representation. There are some signals which are periodic, but they don't have Fourier series. But those signals which are periodic and they don't have Fourier series, they are just mathematical signals. We usually don't encounter such signals in practical systems. So all we can say now is that in continuous time, all realizable periodic signals have Fourier series. So this was a little bit revision of what we were talking about before midterm. Now let's talk about some of the properties of Fourier series. Properties of continuous time Fourier series. We will talk about another Fourier series which is used for discrete time signals, and that will be known as discrete time Fourier series. Right now, we are focusing on continuous time Fourier series. So once we go through these properties, you will find out that depending upon what type of operation is applied on given periodic signal, we will find out what will happen to its Fourier series. And those properties will help you to solve many problems. So sometimes if you are solving a problem related to Fourier series, and if you know about Fourier series properties, then it will be very convenient for you to solve that problem. If you don't use these properties, you may be able to find the answer, but it will take a lot of time. So it's very important that you understand and learn the concept behind these properties. So before talking about the properties, let me introduce the notation that we will be using. So whenever we will relate a given periodic signal to its Fourier series coefficient, so we will be using this notation that x of t, and then this double arrow, Fourier series coefficient, and then on top of that we will say Fourier series. So this notation is usually used to represent that periodic signal x of t is related to its corresponding Fourier series coefficient, or you can say x of t and a sub k, they are Fourier series pair. Okay. So this is periodic signal, and its corresponding Fourier series coefficient, and this notation means that they are paired together. So let me start with the first property, and that is linearity. So let's consider two signals, x of t and another signal y of t. And they are two different signals, but they have same period, okay? They have same period. And let's assume that their period is. Now this signal will have its Fourier series coefficient, let's say represented by a sub k. And this signal y of t, it will have its own Fourier series pair, and let me represent that with pk. Now, if we make another signal that is a linear combination of x of t and y of t. So let's assume that we multiply x of t with some constant a, then we add it to y of t, and y of t is also multiplied with some constant, let's call it b. So this is going to be another signal, and let me call it z of t. So z of t is a linear combination of two signals, x of t and y of t, such that they have the same period, capital T. So according to the linearity property of Fourier series, this new signal z of t, its Fourier series pair, let's call it ck, we can easily relate the Fourier coefficient of this signal to the Fourier coefficient of this signal and this signal in this manner, that if z of t is the linear combination of x of t, so its Fourier coefficient will also be a linear combination of the Fourier series coefficient of x of t and y of t. So I will say what will be the relationship of ck? Ck will be equal to constant a into Fourier coefficient of x of t plus constant b multiplied with the Fourier coefficient of y of t. This is what is linearity property. The Fourier coefficients, they obey the linearity property. If given signal z of t is a linear combination of any number of signals, accordingly, its Fourier coefficients will also be the linear combination of the corresponding Fourier coefficients of the signals that are used in the linear combination. Now, one thing that you need to practice and you need to understand is that you don't need to remember, you don't need to you put this result in your mind and try to remember it in your examination. You should try to understand from where we get this result. So there is always a proof behind any given property. So later on in this course, when we will talk about other tools, that is discrete time Fourier series, and then we will move on to Fourier transform, continuous time Fourier transform, discrete time Fourier transform, and then Laplace transform. So all of these tools, they have properties. So sometime I will not be deriving all of the properties. So I just want to give you an idea that all of the properties of given tools, they can be easily proven. Okay. So to give you this concept, so let's find out how we can get to this result. So let's assume that we are given this signal z of t, which is a time x of t plus b time y of t, and now we want to find out what is the Fourier coefficient. So I say ck. So let's assume that we don't know what is ck equal to. Okay, so let's prove this particular property. So we already know that this signal ak, x of t, and bk, what is the relationship between ak and x of t? So ak will be equal to 1 over t integration over 1 period, and then x of t is to power minus jk omega naught t d of t. Similarly, what is the relationship between bk and x of t? So bk is equal to 1 over t integration over 1 period y of t e to the power minus jk omega naught t d of t. So based on this, if I want to find out what is the relationship of ck with z of t, so I will say ck must be equal to 1 over t integration over one period z of t e to the power minus jk omega naught t. But we know that this z of t, it is equal to this thing. So let me substitute this value over here. So we will say c sub k is equal to 1 over t integration over t a times x of t plus b times y of t e to the power minus jk omega naught t. So I can easily rearrange this equation. So let me split this. So I get a 1 by t integration over t x of t e power minus jk omega naught t d of t plus b then 1 over t integration over t y of t e power minus jk omega naught t d. So I can easily rearrange this equation in this form. And now you can clearly see that this expression is nothing but Fourier coefficients of the signal. And this is nothing but Fourier coefficients of y of t, which we represented as bk. What we get? Ck is equal to a times a sub k plus b times b of k. And this was exactly what we were looking for. So you can see that I have proved this property right in front of you. So later in this course, whenever I mention any property, you should be always capable to prove that property in 2 or 3 steps. Okay. Let's move on to next property. So this was property number 1. So let me move on to property number 2. Property number 2 is conjugation property. Conjugation property. So let me first introduce this property, and then we will find out how to prove this property. So according to the conjugation property of continuous time Fourier series, if you have a signal x of t and its Fourier series pair is a sub k, if you take the complex conjugate of the signal, let's represent it with x conjugate t. So according to this property, the Fourier series pair of this new signal will be equal to a sub minus k conjugate. A sub minus k conjugate. So let's try to prove this property. Okay, so what could be the proof of this property? So the Fourier series relationship between ak and xt is, so let's say ak equal to 1 over t integration over t x of t e power minus jk omega naught t df. This is the relationship that we have derived. Now, Let's take the complex conjugate on both sides. So complex conjugate of left side, and then complex conjugate of right hand side. So we get x conjugate t. When we take the conjugate of this e power minus jk, it will become e power plus j k omega naught t. Now, if you compare this with the standard equation, it's obvious that in the standard equation, we should have minus over here, but over here we have plus. So let's replace k by minus k. So I'm going to replace k by minus k on both sides so that it doesn't affect the result. So on the left hand side, it will become a conjugate minus k 1 over t integration over t x conjugate t, and it will become e power minus jk omega naught t. Now, if you compare this result with the standard equation, so according to the standard result, this is the signal and this is the Fourier coefficient. And now if you compare this, this is our signal and this is the Fourier coefficient. And now you can see what is the Fourier series coefficient of x conjugate t? It is a sub minus k conjugate, exactly this. So if x of t has a Fourier series coefficient ak, what is the Fourier coefficient of x conjugate t? It is a conjugate minus k. Exactly. Now there is additional property that we can easily derive from this conjugate property. Let's assume that given signal is periodic. Okay. So now I will say if x of t is real. So we know that if x of t is real, then x of t must be equal to x conjugate t. So from complex number mathematics, you know that if given number is real signal, then even if you take its conjugate, there will be no difference between the actual signal and its conjugate. So x of t must be equal to x conjugate. Now, based on this property, what is the Fourier coefficient of this signal? Fourier coefficient of x of t is a. And what is the Fourier coefficient of x conjugate t? It is a conjugate minus k. So what is the Fourier coefficient of this? It is equal to a sub minus k conjugate. So if x of t is equal to x conjugate t because of signal is real, then of course their Fourier series coefficients will also be equal. So now for real signals, Fourier coefficients will have this relationship that a sub k must be equal to a sub minus k complex conjugate. And sometimes we also write this equation. If you take complex conjugate of this equation again, so you get a sub k conjugate on the left hand side and a sub minus k. So this conjugate will cancel out with the other conjugate that we take. So for real signal, a k conjugate will be equal to a minus. Let's move on to the next property. time reversal. Time reversal property. According to this property, if given signal x of t has a Fourier series pair A sub k, if you apply time reversal to the signal, so it means x of t becomes x of minus t. So according to this property, the Fourier series coefficient of the signal will also become A sub minus. So let's again, if someone wants to prove this property. So AK is equal to so x of t, and this is the Fourier coefficient, corresponding Fourier coefficient. Now, the other signal that now the signal that I want to find the Fourier coefficient is this one, x of minus. So what is going to be the Fourier coefficient of this signal? So x of minus power integration over one time period. Let me call this Fourier coefficient because we have a different signal. So the Fourier coefficient will be, let's call it A dash sub. So let me replace this minus t by some other dummy variable. So let's say let tau is equal to minus t. So because in this original expression the variable is t, and now we are changing it to tau, so we have to change the interval of integration as well. So let's assume that we are integrating from over a time period t, and let's assume we integrate from 0 to capital T. Okay. So when t is equal to 0, so when t equal to 0, tau will be equal to 0. And when when t is equal to capital T, then tau will be equal to minus t. And this also means that d tau will be equal to minus t. So let me change the variable. So we get Fourier coefficient A sub k dash is equal to 1 over t. And now the lower limit is 0, upper limit is minus t. We have x of tau. Then we have e power minus j k omega naught. So this has become plus, okay, because of this. And then we have minus d of, because you can say dt is equal to minus t. Now I can remove this minus sign by changing the lower limit to upper limit, upper limit to lower. So what will happen to the expression? Fourier series coefficient ak dash will become 1 over t. Now we have integrating from minus t to 0, x of tau e plus jk omega naught tau d. Now I can write this expression as 1 over t minus t to 0. Now, another point that you need to understand is when we use this expression to find the Fourier coefficients for any periodic signal, the integration interval should be equal to the time period of the signal. And it doesn't matter from where we start. So I can start from 0, then I have to stop at capital T. If I start at capital T, I need to stop at 2t. So you can see that in this expression, the interval of integration is from minus capital T to 0. So even then, you can clearly see that this whole interval is equal to the time period. Let me write this expression in a form that will get us to this final result, this one. So I can write this result as e power minus j minus k omega naught tau. Now, if you look at this expression, this is exactly this expression. Of course, it doesn't matter if you represent the variable by t or tau, doesn't matter. So x of tau, x of t and x of tau, there is no difference. Okay, we just change the variable. So you can clearly see that in the original expression for ak we have e power minus j, and now we have e power minus j minus k. So this thing, this whole expression in this red color, this is nothing but a sub minus k, as if you have replaced this k by minus k. So if this expression is a sub k, this expression must be a minus k. So we have found that a k dash is equal to a minus k. But if you remember, what is a k dash? A k dash is the notation that I have used to represent the Fourier coefficient of this signal. So what is the Fourier coefficient of x minus t? It is a k dash, and now we have proved that a k dash is equal to a power minus k, which is exactly this. Let's move on to the next one. Time scaling. So if given signal, which is periodic with period, fundamental period capital T, and its Fourier series pair or Fourier series coefficient is ak. Then if we apply time scaling operation to this signal, so x of 8. So the Fourier series pair for this new signal, which is the time scale version of the original signal, the question is, what will be the Fourier series coefficient? And the answer is, there will be no change in the Fourier series coefficient. Now, let's find out what is the reason why, when you apply time scaling operation, the Fourier series coefficient doesn't change. Now, important thing to remember is this, we have covered this thing maybe in the first or second core lecture. So this A is going to decide what is going to happen to this signal. So for this particular discussion, let's assume that we have a case where the magnitude of A is greater than 1. And if you remember, when you have this sort of situation, it means we are actually compressing the signal. And what will happen? So if this signal if this signal is periodic with period capital T. So of course, when you compress the signal, its time period will change. So it means this signal, its period will be different. It's let me call T dash. And what is going to be the relationship of T dash with this capital T? It will be equal to capital T divided by A, because signal is going to be compressed. So when signal is going to be compressed, time period will reduce. So T dash is T divided by A, where A is a number greater than 1. So capital T will be divided by a number greater than 1, so it will be a number which T dash will be less than. As well as if this signal, its fundamental frequency is omega naught, so this new signal, its fundamental frequency omega naught dash, it's also going to change, and it will be equal to A time omega naught, because time period will reduce, so it means fundamental frequency will increase. Now, if let me go back and compare this situation with over here. When you perform time reversal, so the period of the signal doesn't change. So if this signal period is capital T and its fundamental frequency is omega naught, so this time reverse signal, its period will remain unchanged. So this x minus t will also have the same period, and as a result, its fundamental frequency will also remain the same. But now you can see that when you apply this operation, then time period will change, as well as omega naught dash, that is fundamental frequency, will change. Now the question is, what is going to be the Fourier series pair of this? Okay, so we can make use of the same result, that the relationship between AK and X of T is, so general relationship is Fourier series coefficient AK are represented by this form. So we are interested in finding out what is the Fourier series coefficient of this. So let's assume that we don't know this result. So this is a question mark. So the Fourier coefficient of this signal, let me represent it with some different symbols. So let's call them AK dash. AK dash, which is the Fourier coefficient of this signal. So I'm going to replace this signal with x of power minus jk by t. Let me introduce a new variable. So let's say let a t is equal to tau, which will mean that dt will be equal to d tau by a. Also, because I'm changing the period, so this integration will be over the period of this signal. What is the period of this signal? It is t dash. So let me say this is t dash. So it means in place of t dash, I can say t by. Let's say if we are integrating over one period of t dash, so this is going to be from 0 to t dash, and t dash is equal to t by a. Okay. And now x of at it become x of tau. Let me also use this one. So this is omega naught is not correct. Omega naught dash is the period of this. Okay. So I will get e power minus j k Omega naught dash will become A time omega naught, this relationship. And this T, I can replace it. T can be replaced by tau by A. This dt will be replaced by, as I mentioned over here, it will be d tau over A. And now the important point is this: these limits are with respect to t. Okay. So now I have to change the limit. So we have this relationship that A t is equal to tau. So when t is equal to 0, when t equal to 0, it means, so I will say for t equal to 0, tau will also be equal to 0. And the upper limit of t is capital T by A. So when t becomes equal to T by A, as a result, what will be the limits with respect to tau? It will be simply equal to T. So as a result, this lower limit will remain same, but T by A will become T. So this is A dash. Now this A will cancel out with this. This A will cancel out with this. So finally, we are left with, so what is the resultant expression for AK dash? Let me do it over here. So AK dash is equal to 1 over T integration from 0 to T x of tau e power minus j k omega naught tau d of t. Now this expression, this result is exactly this one, which is AK. Now you should not get confused that we have T over here and we have tau over here. This whole result doesn't change whether you use this variable T or whether you use the variable tau. If you look at this expression and this expression, they will give you the same result. So it means this right hand side is exactly AK. So now the Fourier series coefficient. So let's say that we were looking for that xat has a Fourier series coefficient AK dash. And we have proved that AK dash is exactly equal to AK. This is the result that we introduced at the start, that when you apply time scaling operation to a given signal, its Fourier coefficients remain unchanged. Now, you should remember this point as well, that even though Fourier series coefficients remain unchanged when you apply time scaling, but the Fourier series representation will change. Why it will change? Because signal time period has changed, because signal fundamental frequency has changed. So Fourier coefficients remain unchanged, but Fourier series representation will change. That is an important point that you can get from this whole discussion. Let's move on to the next property. So we are now looking at the fifth property. Time shifting. So x of t having Fourier series pair represented by a sub k. If we introduce time shift, so now x of t become x of t minus t naught. This is how we represent the time shifting operation mathematically. So what is going to be the Fourier series coefficient of this signal? So I will going to write the result and then I will prove it. So the Fourier coefficient of this signal will be equal to the Fourier coefficient of the original signal multiplied with e power minus j k omega naught t naught. So this factor is going to be multiplied with the Fourier series coefficient. So what is the effect of time shifting on the Fourier series coefficient? The Fourier series coefficient get multiplied with this particular exponential factor e power minus j k omega naught t. Now you can generalize this result because I have minus over here. So you can see this is kind of a delay operation. So that is why we have minus one. But if it is let's say it is x of t plus t naught, which means it is advance operation. So as a result, you will have plus over. So it means minus plus, accordingly, we have minus plus over. So the factor will remain the same. Only the sign, I'm talking about the sign. So minus t naught, you get minus over. If you have plus t naught, you get plus t naught over. Now, what is the proof of this property? So let's find out that what is the Fourier coefficient of. I'm going to go back to the equation that I want to prove. I want to prove this result. And once you understand this, you can easily prove this for x of t plus t. So again, I'm going to represent the Fourier coefficient of this signal as ak dash. So what will be the expression for ak dash? Ak dash will be calculated based on this result. So 1 over t, integration over t. And the signal is x of t minus t naught. So we have e power minus j k omega naught t. So let's replace this t minus t naught equal to tau. Okay, t naught is a constant number. So dt will be d tau. And again, these limits are with respect to t. So lower limit is, let's say, 0, upper limit is t, tau, sorry, capital T. So let's see what are the limits with respect to tau based on this equation. So for t equal to 0, tau will be minus t naught. And for t equal to capital T, tau will be equal to t minus t. So these are lower and upper limits with respect to tau. So now coming back to this, again, you should remember this thing, even though this is a new signal, which is the time shifted version, but when I'm finding the Fourier coefficient, I'm using the same period. This capital T is the period of this signal as well as this period, because we know when you perform time shifting operation on any signal, its period remains unchanged. So what are the lower limits with respect to tau? So lower limit is minus t naught, and upper limit is t minus t. And you can easily verify that this whole interval, this upper limit minus lower limit, is equal to capital T. So again, we are integrating over one period of this signal. Then we have x of tau e power minus jk cannot in place of t. Now we have to make use of this. So what is the expression for t? T is equal to t naught plus 2. So t is replaced by t naught plus 2. And then this dt, and dt is replaced by t. Now you can see that this integration is with respect to tau. But you can see that there is one term, that is e power minus jk omega naught t. This whole term is constant. So we can take this out of this integration sign. So what we get, so we have e power minus jk omega naught t. This term I can take out, and we are left with this term integration with respect to minus t naught to capital T minus T naught, and then this x of tau e power minus jk omega naught tau d of tau. So this is d of tau. So this is d of tau. Now, if you look at this, of course, this is the limit as well. This is nothing but Fourier coefficient AK for this segment. So, what is the result? Result is Fourier coefficient AK dash are equal to this factor e power minus jk omega naught t naught, and this whole thing is AK. And this is the result that we mentioned before. So when you apply time shifting operation to a signal, what happened to its Fourier coefficient? The Fourier coefficient gets multiplied with this factor. Let's move on to another property which is related to frequency shift. So now, rather than talking about shifting operation in time domain, we are talking about shifting operation in frequency domain, which means that if x of t has a Fourier series pair represented by a sub k, if we perform frequency shifting operation, it means this Fourier coefficient AK, let's say AK, it becomes AK minus M. So the original Fourier coefficient, which was at K, now it has moved to a new place, K minus M. So this M is going to decide how much frequency shift has been introduced. And now the question is, what is going to happen to the signal in time domain? So let's find out what is this signal. In other words, if AK is the Fourier series coefficient of x of t, so what type of signal will have this Fourier coefficient, which is AK but shifted by some frequency? Okay. So we can easily find this with simple proof. So the relationship, so keep this thing in mind that the standard equation is so Fourier coefficient AK it has this representation. So what is going to be the representation of this new Fourier series coefficient? So I will say Fourier coefficient a k minus n must be equal to 1 over t integration over t x of t and then e power minus j, and now I'm going to replace k as k by minus n. I will say e power minus j k minus m. Let me usually use small letters, so let me use this. This is small n. Okay. Similarly, this is also small k. So we end up with this. Now I can rewrite this equation. 1 over t kx of t, and then I will say e power. Let me this minus this plus, we get e plus j m omega naught t and e power minus jk omega naught a sub k. Now, if you look at this expression, it is obvious that this is the signal for which the Fourier coefficient is this. If you look at this, again, I'm repeating this statement again and again, but it's very important. When you take the, when you look at the standard expression, so the term that is beside e power minus j omega naught t, so this is the signal for which Fourier coefficient is written on the left-hand side. If you compare this standard equation with this equation, so you can see what is written with this exponential factor. Previously is what x of t, and this was the Fourier coefficient. And now what is written beside this? It is this whole thing. So this is the signal for which the Fourier coefficient must be on the left-hand side. So now I can remove this unknown, that whenever you perform frequency shifting and Fourier coefficient ak becomes ak minus m. So what is the new signal in time domain? It is the original signal multiplied with this factor e plus j m omega naught. So this is clearly telling us that depending upon how much frequency shift is introduced, so we have the same factor over here. Let's move on to the next property. Now I'm moving to property number 7. Property number 7 is related to multiplication, and this property is also related to convolution as well. Okay, so let me first talk about multiplication property, and then we will move on to convolution property, and then see the relationship between these two properties. So according to multiplication property, if you have two signals which are having the same period, so let's say x of t having Fourier series coefficients represented by ak, another signal y of t, and this signal has the same period as x of t, and its Fourier series pair is bk. Now, if you multiply these two signals together, it means if you multiply x of t with y of t. So that is why it's multiplication property. So multiplication of these two signals will result into some other signal z of t. And because both of these signals are periodic with period t, so when you multiply two signals with the same period, so as a result, z of t will also be periodic with the same period. Now the question is, what is going to be the Fourier series pair for this new signal, which is formed by the multiplication of two periodic signals. So let me represent the Fourier coefficient by Ck. So, and let me write the property, and then we will try to prove it. So the Fourier coefficient of this signal, Z of t, which is the product of two signals, it is equal to the convolution between the Fourier coefficients of x of t and y of t. It means it has to be equal to AK convolved with B. So the multiplication operation in time domain results into convolution operation in the frequency domain. Now, how to prove this property? So let me write the Fourier series representation of this signal in terms of k. So for this signal, I will say x of t. Its Fourier series representation is ak e to the power plus jk omega naught, where k is from minus infinity to plus. And for this signal, I will say y of t can be represented in terms of its Fourier series representation as e plus jk t, where k is from minus infinity to plus infinity. Now, in order to prove this property, let me change the variables so that we can arrive at the result that is this. So in the first expression, let me replace k by some other integer. Let me call it n. And in the second expression, let me use m. So now the expression is in terms of n. So you have an, and then you have n over here. This expression is with respect to, let's say, another integer, small m. So we accordingly, this coefficient will become dm, and we have m over here. So you can see this substitution is not going to change the overall result. This is still the Fourier series of x of t, and this is the Fourier series of y. So what we are looking at, we are going to multiply these two signals together. Okay, so it means x of t, y of t. So when you multiply them together, so as a result, on the right hand side, we are going to multiply their Fourier series representation. So we have this thing. And we have Bm. Let me, so this thing, of course, I'm calling him, this will result into Z of t. So we have n from minus infinity to plus infinity, then m from minus infinity to plus infinity, and then we have an, bm, and then we can combine these two exponential functions, this one and this one. So when you combine them together, you will end up with e plus j n plus m omega naught t. And now let me introduce a new variable. So let's say that k is equal to n plus n. K is equal to n plus n. And now I'm going to change the limit. So let's say in the first expression, the variable is n. So let's find out what is the value of k corresponding to this. So when n is minus infinity, so the lower limit with respect to n is minus infinity. So as a result, k will also be minus infinity. And when n is equal to plus infinity, so when you put plus infinity over, k will also be equal to plus infinity. K will also be equal to plus infinity. So it means this first summation, if I change the variable from n to k, so even then the limits will be from minus infinity to plus infinity. In place of m, so if you use this, so I can say m is equal to k minus m. So this will become b k minus m. And you get e plus j, n plus m is replaced by k. So you get k omega naught. Now, if you look at this expression, you can clearly see that when you look at this expression, so anything which is beside this exponential term is the Fourier coefficient. So in this standard expression, we will say that these are the Fourier coefficients of this segment. Similarly, if you look at this, what is the term beside this standard term, e plus j omega, e plus j m omega naught t, it is bm. So you will say this bm is the Fourier coefficient of y. In a similar logic, if you look at this, what is the standard term? The standard term is this one, e plus j k. So what is written beside this? It is this one. Let me correct the mistake over here. So let me remove this thing, this final result, which I now, this is what I was trying to do, that in place of this k plus m, sorry, n plus m, I introduced another integer, that is k. And then I'm going to replace this particular summation, which is with respect to m, and now I want this summation to be with respect to k, with respect to k. So based on this relationship between k and m, so it's obvious that when m is minus infinity, k will also be minus infinity. If this m is plus infinity, this will also be plus infinity. So when I change this summation from m to k, the lower limit will be minus infinity and upper limit will also be plus infinity. Okay. So this is what I'm going to do is, so let me mark this. This particular summation is now be replaced in terms of k. In terms of k. Okay. So let me move to the next slide. So z of t, which is actually the product of two signals, x of t, y of t, and it's going to be represented by, so we have k from minus infinity to plus infinity. The other summation is with respect to small n. Okay, so this is this same one, and now this is replaced in terms of k. Then we have an. So this is n, and now I'm going to, because I have changed the variable m, so this b m is going to be in terms of, so m is now k minus. We get b sub n minus k. And then we have, of course, this is now e plus j k. So we have E plus j k omega naught. So now if you compare this result, this is the signal for which we are finding the Fourier series coefficient. So An is the Fourier coefficient of x of t. Bm is the Fourier coefficient of y of t. And now when you multiply these two signals together, you get a signal z of t. And what are the Fourier coefficients of this signal? These are the Fourier coefficients. So we have a of n, b of n minus k, where n is from minus infinity to plus infinity. And now those students who remember convolution, this is actually the convolution. So what is actually this thing? This is the convolution between Fourier coefficients ak with b. So this is which I wrote over here, that the Fourier coefficient of this signal, which is the product of two signal, is ck, and ck is nothing but convolution of ak and bk. Now what is the convolution? If you remember, convolution operation in discrete time is represented by this. So a of n, b of n minus k is actually convolution. This is the proof of this property.